So I have shared with you two presentations, two video presentations along with the study material. Have you received those?
Yes, sir.
Yes,
So
sir.
you must cover those, because some of the derivation that we will be doing tomorrow, for that those background is needed.
Sir, we will be having class on 2nd October. No, that is tomorrow.
Yes, yes. Tomorrow is a holiday.
Yes, sir.
Okay.
2nd October, sir.
Acha, acha, acha.
Gandhi
Okay, okay,
Jayanti.
okay. Acha, acha, acha. Okay, okay. So then Saturday I will take class. Saturday I will take class. Okay. So let's start. Can you see the canvas screen?
Yes, sir.
Yes.
Yes, yes, yes. So I am drawing. What is the curve that I am drawing? I have marked by tick to double tick. What is the typical curve that we see here?
Engineering stress strain.
Engineering stress strain. Yeah. From say this is a very interesting answer that you have given. Engineering stress strain. Okay, that I understand, but can you say more specifically?
For a ductile metal.
Ductile material.
Ductile materials. I may also see some other curve for ductile material. So
this is
neither
for uniaxial tension.
uniaxial tension, right? So you should give the answer engineering stress strain curve for ductile material under uniaxial tension, because in tension test we see this curve and not necessarily for the same material. You prepare a compression specimen which is a cylindrical type specimen, and if you apply compression, not necessarily that you will get the same stress strain curve. Okay. Do you get the same stress strain curve if you do a compression test?
No, sir.
No, sir.
And how the curve would look like?
It will go.
Sir, it will go the negative x-axis side, some portion.
That is a different issue. That you are right, that I should draw a negative axis and draw on the negative, but let us consider that also in the same scale. Okay. You are right that we should draw it in a negatives because it's a compression. But if I draw on the same scale, I take absolute value of stress and strain, then I can draw on the same scale. So will the nature of the curve be same as the curve we are drawing here?
Sir, nature will be reversed.
No, sir.
No, sir. Cross section.
So how the curve will look like? It will come down or go up?
Go up.
Can you explain why I am drawing this kind of a curve? And what is this curve nature? Here I am drawing engineering stress strain curve for compression test. If this is the tension test, then this is the curve for compression test. And it is engineering stress strain curve. It is also ductile material. So if you give an answer that you expect this curve for engineering stress strain of a ductile metal, why not this curve? This is also engineering stress strain curve for ductile metal. But the curve nature you see is completely different. And why different? How do you explain it?
Sir, in engineering stress, we consider the initial cross section area. But during
so
the
what is happening? Yes, in compression testing
increases. During the testing, cross sectional area increases. But for the calculation of engineering stress, we are using the initial cross sectional area. So the stress engineering stress we are calculating is higher than the
So
actual.
in tension, cross-sectional area decreases. In compression, cross-sectional area increases. But still, if you draw engineering stress, you consider the initial cross-section only. It's not that in tensile engineering stress strain curve, in tensile test, we consider the cross-sectional area of the initial, and in compression, we do not take. If you draw drawing engineering stress, that always the initial cross-section A0 will be considered. So your answer is wrong. Initial area A0 will always be considered, whether you draw in tension or in compression, if it is an engineering stress plot. So you have to explain what is happening in tension and what else is happening in compression.
So in tension, necking is
different
happening,
mechanisms.
and in
Yes,
necking
in
compression,
tension, necking happens, right? In tension, necking happens. And you know, because of necking, why your curve drops in tension? Why your curve drops in tension? Because you know the material continuously strain hardens. That we have explained you before. But due to necking, the decrease in cross-sectional area is so much rapid that strain hardening can be maintained. That is, stress increases, true stress increases, even if your load comes down. You remember the previous discussion that we had? You remember that? That ultimately the nature of the curve is dictated by the term load, right? P. So in tension stress strain curve, because of necking, your cross-sectional area decreases very rapidly. And because cross-sectional area decreases very rapidly, what happens? Your true stress goes up, even if your load requirement come down. So this decreases very rapidly. You remember the previous discussion we had one day? We have considered some values.
Yes, sir.
Yes, we considered 24 something, no, 10. So from that, and that is happens in tension, and that doesn't happen in compression. Because in compression, your cross section is continuously increasing. So you can see that what is the difference that I am drawing here. In tension, I am showing fracture here. In compression, I am showing fracture at a much higher strain. Will it be true or not? Will that happen or not? For ductile metals?
Yes, sir.
That happens. So suppose steel, I take a normal mild steel, you will get say elongation to failure 25%. Do you know if you apply compression, what will be the elongation to failure? A decrease in height to failure? If in tension there is elongation, then in compression there will be reduction in height. So what would be the percentage reduction in height? You guess? You want to guess? You want to guess a value? It will be more than 90%. More than 90%. Why? What is the difference? Hello?
So it doesn't go to failure because of necking.
Yes, because tensile specimen, why it fails? Because it is necking. So necking leads to decrease in cross section, and whenever there is a decrease in cross section, the area where cross section is lower, the rate of decrease becomes higher at that particular location. The rate of decrease becomes higher at that particular location. So in a very rapid rate, it decreases. At a very rapid rate, cross-sectional area decreases because their stress becomes high due to the low cross-section. So in tension, the problem is necking, because necking happens. So by the process of necking, localized deformation happens, and every deformation is happening in one region. Crack, voids form and void grow and void coalesce, and then crack forms, and then crack leads to failure. But in compression, necking doesn't happen. And the answer that I have received so far is a part answer. Who can say the other part of the answer? Why we can apply much higher deformation in compression than in tension? What is the second reason? In tension, necking is a problem. What is the second reason?
Cross-sectional area get increases, so higher load is required.
That load is high. Load is required, that is fine. Load is required, that is fine. But higher load is required, that is fine. But here I am not considering the cross section. I am considering the initial cross section, as I said. So still, anyway, first you answer this. Let us finish that part. That why in compression we can apply more deformation. One reason is in compression necking doesn't happen, and what is the second reason?
So buzzing will take place in compression.
Ulta pulta bol raha. Second reason is
No
if there
sleep,
is
sir, no.
if there is a no slip, if there is no slip, then how you get so much of deformation? If tension you get plastic deformation, then compression also you get plastic deformation. And I said that more than 90% reduction in area is possible. So if you start with a cylinder, you can end up with a big plate if you apply compression with a very small thickness. So there will be a huge amount of plastic deformation. Who can say what leads to other reason that leads to failure in?
Hello, sir.
Yes, tell.
Sir, if there is any internal crack or defect in tensile load, it opens up, but in compressive load, it closes.
What is your name?
Rashid, sir.
Rashid, very good answer you have given. That is the right answer. If there is a defect formation, suppose the 2-3 voids coalesce and they form a small crack. Crack always grows in tension. Because if there is something like this, how it can grow if you apply tension? Then it will try to stretch. You do one simple experiment. You take a A4 size white page, you take a scissor and make a small cut, and then try to expand the cut. What kind of loading you need to apply?
Tensile.
Isn't it? If you want to tear a page, then the loading needed is tensile. If you do not apply tensile, it will be very difficult to tear a page. So, crack propagation happens under tension. And what compression will do? Compression will close down the crack. If there is a crack form, compression will try to close it down. So if there is a constant compressive stress, then monotonic compressive loading, then the crack growth will be very difficult. Until and unless some other mechanism leads to cracking, which happens in compression tests. Because I can ask a question, okay, in compression, if you can apply so high deformation, then why not 100% or 99.999999%?
Sir, secondary tensile forces arises in the
Secondary
in case of
tensile
compression.
force, you are saying right, but you know what is secondary tensile force? If there is bulging, suppose this is, I am showing bulging. Whenever there is a stretching, that causes cracking. So you will find in a bulged component, like you see stretch marks, it's something like that. Whenever some region is getting bloated, then there will be a tensile force, and that is secondary tensile stress. But secondary tension, but also is cross-sectional is increasing. So the crack that will form, will those secondary cracks lead to failure? Answer is no, because when you apply compression, there will be a lot of shearing involved, lot of shear. So it will be a huge amount of shear deformation at 45-degree angles, and gradually along those shear bands, strain accumulate, and therefrom you will see shear kind of a failure. So that is the reason, if I give you a cylinder, you cannot thin it down to 1 atomic layer thickness. Otherwise, I could have given you a small cylinder and asked you to compress, and you could have reduced it to 1 atomic layer. But if it becomes too thin, then there are shear cracks along the shear stress. Too much deformation along certain shear bands leads to separation of metal. But that will happen at a very high amount of deformation, more than 90-95%. So what is the conclusion of this story? Why I am saying these things? The difference in tension and compression, why I am saying these things? From your application point of view, application of something, why is it important? Now you conclude.
Compressive strength is more than tensile.
Compressive?
Compressive stresses are beneficial.
Compressive stresses are beneficial. That's why we can apply much higher amount of deformation in compression than tension. So now from coming to the real world application, you always have to think about application, right? So now you tell me what conclusion you make from that, from this thing.
Like when we try to form a metal into any shapes, we should apply compression more. Like,
what is your name?
Adarsh Mishra.
Others, your answer is good. I liked your answer. Basically, when you need...
Sir, in wire drawing application.
No, in wire drawing, we do not... that is also compression. That is also compression. That is called secondary compression, right? Wire drawing is also secondary compression. There also deformation is compression. What about rolling? What about forging? Do you apply tensile force or compressive force in rolling, forging?
Compression.
Compression. Direct compression. Right. I forgot the word. Direct compression. What is extrusion and wire drawing? What kind of compression are those?
Secondary.
Indirect compression. Indirect compression. So what is the conclusion? That if you want to reduce, if you want to do working on metal, it's always better to go for a compressive process. Only tensile process is used in stretch forming, and a part of deep drawing where we want to draw a cup, there we need to rely on tension. Otherwise, majority of the mechanical working processes are compressive processes. If someone asks you, because I can give you a big metal piece, right? I can give you a block and I can ask you that, yes, you come up with a structure like this. So there are two possibilities. One possibility is you can apply compression like that. But I can ask you why there is a need for compression. You can put you can apply tension also. By tension, you could also have done that. If a big metal piece you take and apply a tension, then also it will thin down. But it will not happen because before that breaking, and in tension, applying deformation is also difficult. It is more easy in compression because the entire piece you need to take and stretch. But in compression, you can do rolling part by part. Suppose you do rolling of this end only, reduce it, and then you extend the metal. You understand? Every time in rolling, what does it look like? There are two grooves and you push the metal through. So first the initial part will be rolled, it will go like this, and then you continuously feed it. So every time a small segment of metal you are deforming by compression. You are doing it in segments, small segments you are doing, continuously push it from that side, continuously pull it from that side. So that is your rolling. Could you understand?
Yes, sir.
Yes,
So
sir.
that is why majority of our deformation processes are compressive processes and not tensile processes. Very important. Now in tension, when you do a tension test, you get an elongation, and we divide the elongation in two parts, you know. One is uniform elongation and one is post-uniform elongation. So you tell me, what is the benefit of uniform? What is the importance of uniform elongation? Sometimes people consider uniform elongation only for certain purposes. Why uniform elongation is important? Because if you want to draw a cup or if you want to draw an utensils by a deep drawing process which is tension, what cross section you want? What is your requirement? You may draw a very thin sheet, but or an aircraft body that is also stretch forming. The sheet is stretched like this, thin sheet. So what is your requirement there? You want uniform deformation. You want, okay, it gets stretched, but everywhere the thickness remains the same. Do you want necking? Do you want some, you buy an utensils from a shop where a part is thick and another part is this much thin? One day which will lead to leakage of your container. Do you want it? No.
No, sir.
You want uniform thickness, uniform thickness. You want uniform thickness, and that's why when we do forming operations, even if we apply some tension processes, stretch forming, deep drawing, we have to deform up to this point, and we should not cross this point, because in that case, under tension, there is a possibility of necking. And from the necking, when you pour in your Coke or Pepsi or whatever beverage, under pressure, that portion will leak. So that is the importance of uniform elongation. And what ensures good uniform elongation?
Strain hardening.
What is your name?
Sir, Jyoti Ranjan.
Jyoti Ranjan, your answer is good answer. So strain hardening. Now Jyoti Ranjan, can you tell, how do you know that uniform elongation and strain hardening are related?
Sir, we are previously derived an expression that uniform elongation equal to n in order to prevent necking.
Very good. So that is the answer. So you know the importance of n now from application point of view. If you want to draw an utensils, if you want to draw a cup or something, or this Milton water bottles, these are also drawn. The cylinder is drawn basically. You need to ensure n value remains very high, so that uniform elongation is also high. You do not want difference in thickness in a very thin sheets. Can you tell me, beside n, another factor also increases uniform elongation? What is that?
Strain rate.
So strain rate sensitivity.
How? I have given you a assignment where you have derived something dA by, what was that? dA by dt. Huh?
Minus dA by dt.
Yes, minus dA by dt equal to something p to the power
1 by m.
1 minus m by m or something like that, no? Something like that. That was the very important equation, because that dictates necking. So it tells, that expression tells, if by chance any location cross section is decreased, by chance this location cross section is decreased, so it is saying the rate of decrease will be more compared to the other region. So the decrease in cross section at other region will be less, and if somewhere cross section is decreased, there it will decrease at an even higher rate, which will continuously increase as the neck grows. So by chance, even if in a piece of metal a small neck has formed, but if m equal to 1, you will find that this decrease become independent of the local thickness. This was P or A? You remember? It was A or P? What?
A.
Anyway, I will show. Huh?
Area, sir.
Area.
Area. So
area.
It becomes independent of the area. Otherwise, if m is less, wherever there is a thinning, the rate of thinning will also be very high at that particular location. Compared to the other region, that location will decrease in thickness at a much higher rate compared to the uniformly deformed part. But if you can make m equal to 1 or high, then that aspect also decreases. So high m value is also favorable. So if you have read NU1 superplasticity, the superplastic material show high M value, high N, high M. So both these factors are beneficial. Strain hardening. Now you understand what is the huge importance of strain hardening. We think strain hardening is bad because it increases the load requirement for deformation. But on the other hand, strain hardening is also necessary to ensure uniform deformation. And that's why we are able to form into uniform thickness products. So from real world, real application point of view, you have to understand the problems. Now let me tell you, post-uniform elongation is also helpful. So if you ideally ask me to draw a curve, I will draw something like this. That is very good. Because post-uniform elongation is also helpful. Why post-uniform elongation, high elongation is helpful? More helpful is uniform elongation. But in some application, post-uniform is also useful. Why? Because suppose inside a body, some defects generated. Suppose a necking has happened. High post-uniform elongation means that material will be able to sustain with that for longer duration. Even if defects form, even if neck forms, if it can sustain, if it doesn't break down, fail, then at least it is holding up your purpose, right? And by that, it will give you more time. By that time, you may be able to detect that defect has formed inside. So basically, the stable crack propagation that happens, it happens during this post-uniform elongation stage. So longer that stage means the material has defect, but with that, it can sustain for long duration. It doesn't fail catastrophically. Because there are pipelines, undersea pipeline, intercontinental pipelines through which oil is transported from one location to the other, crude oil. And those pipelines at any remote location, suppose something happened, a defect form. If it immediately fails there, break into pieces, separates, then entire oil leakage will be there. So even if there is a local thinning for some reason, under sea earthquake or something, then at least if it can hold, you have sensors, and those sensors can able to detect, okay, this thing happened. So before you send your repair team, it actually will survive. Otherwise, it will fail there and entire oil spillage will take place and environment impact. So these are very important things. I am trying to draw a tension test in car. Okay, now last question, sir. Why the engineering stress in compression is higher than tension? Of course, area is increasing, load requirement is increasing, but I am drawing load by area. So I am drawing stress. Why the stress requirement is higher in compression when it is deforming under strain hardening? Or afterwards also. Why the stress requirement is higher? Can you tell? Who can tell? Even the yield point in compression may be little higher. It generally merges with tension for the same material, but it may be or post yield little high, high compared to tension curve. Compression curve remains at a higher side. Why? Who can tell? Very practical sense is needed to answer this. and the gap will continuously grow. Tell, you know.
Strain hardening is high.
No, strain hardening is same. Things are not different. Metal is different. It is not the answer. If you go to dislocation
Hello,
theory, yes, you tell.
Sir, load is continuously increasing.
Yes, load is increasing.
And area
that
is constant.
Yeah. Yes.
Initial area is constant.
No, वो answer नहीं हो रहा है. वो that answer is coming time and again, but something is there in compression which is not there in tension. You think about a compression test and you think about a tension test. Why the stress requirement? I am not talking about load by area. Stress. Even if you tell me true stress will be higher in compression. Why? True stress, if you consider the area change, still that will be higher in compression. Why is that?
So the negative and the positive dislocation may merge.
No. Dislocation theory will not give you answer. Basically, similar thing is happening. You stretch and you
compression.
You are not negative positive. कैसे आएगा? You are only one side deforming, na? Either you are stretching or you are squeezing. So dislocation theory will not give the answer.
Sir, triaxiality is more in compression.
Which one? What is more?
Triaxiality.
No.
Atomic
There are
distance is
friction forces
reduced.
acting in the interface.
Huh?
Sir, more constraint developed.
What constraint? Yes, what constraint? What constraint? Suppose I have taken a platen and inside that I am deforming a piece of a cylinder. Suppose I have platen, I have deforming a cylinder. And this platen comes down. The cylinder spread into like this. You have read mechanical working. Rolling,
In compression, sir, there is a plane strain condition.
That is okay. That is okay. In compression, plane strain is a good answer. But if I use a thin cylinder, then it will not be in plane strain. If it is a very thick plate, then plane strain. But the cylinder that I am drawing, its cross section is not very different from a tension specimen. But of course, cross section is increasing, so that is one aspect. But I'm not getting the exact. Yeah, you tell.
It has to overcome the friction.
What is your name?
Others, Mr.
Others, Mr. सब अच्छा आंसर दे रहा है. For the metal to flow this side in compression, there is a resistance at the interface. There is a resistance at the interface, and against that the metal has to flow because the metal is continuously in touch with the platens. So if it has to flow, what it has to do? It has to work against the friction. It has to work against the friction generated at the interface. And if your platen surface is rough, more will be the friction. If your platen surface is properly lubricated, less will be the friction. So the load that you need in compression is basically the load you need for deformation plus additional load or additional stress to overcome friction. But in tension, friction is not that much because majority of the metal piece, the gauge is not under friction. Only this grip, it is tightly held. Some amount of friction is there at the grip, but the gauge region is free flowing. Isn't it? There is no resistance this side or that side. But in compression, if it has to flow, it has to overcome the friction. So in compression processes, you need to apply proper lubricant. Molten glass, Teflon, graphite, the lubricant that survives at high temperature. Sometime when we do something, we apply, suppose I apply tension and then I apply compression. Suppose I apply tension first in the positive and then I unloaded it and I applied compression. What happens? The yield strength that I get in tension, if I write it as sigma 0, suppose in tension sigma 0 T, when I do reverse loading, I get yield strength on the opposite direction when sigma 0 C. In general, if you uniaxially load them, either tension or compression, these yield strength values remain same. But when you apply tension and then apply compression on the same material, what happens that you will find the first time the yield strength that you get will be higher than the yield strength in the reverse loading. Which will be higher? The yield strength that you get in subsequent tension. Have you heard this phenomena before?
Yes, sir.
Or if you may do opposite also. You apply compression. You apply compression. There you will get a compressive yield strength. Then on the same metal you apply tension. You will find the yield strength is reduced a little bit. Very small, but there will be reduction. Again you do compression, it will reduce further. Again tension, reduce. It will do like this and then stabilize at one point. A point will come after 10, 20 cycle, 50 cycle, it will stabilize. Why does this happen?
Because of back stresses.
Because when you are loading in one direction, you are creating dislocations and those are getting piled up at obstacles. Those are piled up at obstacles. So there is an obstacle, there is a wall against which the dislocations are piled up. Basically, you are making a queue at the ticket counter and there is a push from behind. So at the front of the row, what will happen? They will be under stress and they will try to apply a back stress. Go back, why you are pushing me, why you are pushing me? They will push on the back side. So that is called back stress. Now, if you do a reverse loading, if you reverse your loading, what will happen? That this backward movement will be favored because your back stress will add with your applied stress and movement of dislocation in the reverse direction will be easier. And another reason is if you do forward loading, you create majority of one kind of dislocations, say positive dislocation, right hand screw dislocation. When you do reverse loading, you create a majority of opposite type of dislocation. Negative dislocation, left hand screw dislocation. So some of those negative dislocation will cancel the positive dislocation. Initially, the positive dislocation strain hardened the material, but when you are creating some negative, they will reduce the strain hardening effect also. So these are the two reasons, and this phenomena is called Bauschinger effect. If you apply loading in one direction and if you reverse your loading, then the strength goes down. And again you do reversing, continuously it will go down. Up to a point where this thing stabilizes. That is called stable hysteresis. So what I am showing, there is a hysteresis loop and it will stabilize at some point, which we call stable hysteresis. In fatigue, these things happen. 1 minute, I am coming. Am I audible?
Yes, sir.
Yes, sir.
So will you remember Bauschinger effect? In the book, in Dieter's book, all the books, it is nicely written. Back stress. When you load in one direction, dislocation pile up, that creates a back stress. And back stress help in moving the dislocation in opposite direction when you apply the reverse the loading. Because in reverse loading, the dislocations have to move in the opposite direction. So in reverse loading, back stress helps the movement of dislocation. And also another reason I have told that strain hardening will also go down a bit, because the first time the dislocation you have generated, when you do reverse loading, in general, opposite kind of dislocations will come and they may annihilate each other, cancel each other. One aspect, one question I am asking. Suppose I draw a stress strain curve. Here is your yield, here is your UTS. I draw another stress strain curve. Something like this. 1 and 2. Which one will you prefer?
First one.
Which one will you prefer?
First one.
First one. Why first one? Suppose uniform elongation you are getting even in 2. Somehow it's flowing in a viscous manner. So uniformity is maintained even in 2. But why first one you will prefer?
Sir, in first, it will give indication before fracture.
Acha.
Sharpness is more for first one.
Higher
Which one?
UTS, sir.
Yes, higher UTS. Good, higher UTS.
So more impact energy.
Coming to say, okay, that is good. More energy absorption. Okay, more energy absorption. But here also I can have something like this. I can increase the area under this curve. Suppose this curve. Still, I will prefer this curve. Why? That means if I consider the difference between yield and UTS, I want there must be a difference between yield and UTS. Why we need high UTS compared to yield strength? Can anyone tell?
So that we have some deformation zone.
Sir,
Yes, that is the right answer. Because when I do mechanical working, permanent shape change, on which region I can do? I have to cross yield, but I should not cross UTS, because UTS crossing means necking. So this is my beneficial zone on which I can do mechanical working. So if I apply a stress here, some working, then some more deformation, but I am not in the risk of causing necking. And as it will go very close, I will stop my process. You understand? What is the problem here? To cause permanent, there is a risk that at the same load material can completely rupture, completely fail, because there is no difference between yield and UTS. Yield strength is 500, UTS is 500. To cause plastic deformation, what stress you will apply? You have to apply 501, 502, 510. But there is a risk that the metal continuously flow and fail under that load. But that risk is not there in curve number 1. There you can apply a stress which is higher than yield stress, but you know it is lower than UTS. So no way it will lead to failure. Is it okay? Could you understand my point?
Yes, sir.
Yes, sir.
Okay. I have one request and one suggestion for you. Say I am covering different things from different conceptual, and I may cover just the dislocation theory and end my course. So I have a request that you please consider my request that tomorrow is Gandhi Jayanti, and we all have very high respect for our father of the nation. But with that respect, can we do a class tomorrow? What is your view?
Yes, sir. No.
So you please cooperate with me. I am also teaching you things, and you please also cooperate with me. And you don't complain against me, because it's a big day. So if you complain, some of you will complain against me, I may be in trouble. Okay, but let us take in a true spirit and let us have class tomorrow.
Okay,
because our national development is our priority, right? And Mahatma Gandhi wanted that. ठीक है?
Yes, sir.
सोचो,
Okay, sir.
कंप्लेन कर देना मेरे नाम पर, नहीं तो मैं अभी ट्रबल में हो जाऊंगा.
So,
Thank you.
So,
Yes,
some
yes.
of the students could have problem to attending the class tomorrow. I mean, attendance will be compulsory or not tomorrow?
Now, what problem? You will be traveling or something?
No. If some problem by then.
Yeah. Yes. You may go for, you may have a cultural program or thing. So attendance will not be.
No, sir.
Yeah. Attendance will not be compulsory tomorrow. Attendance will
Sir,
not
what
be
is the
compulsory.
class timing?
Same timing, 11 to 1.
Okay, sir.
Okay, same time.
Okay, sir.
Thank you. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.